Good morning, everyone. I'm Indrani Chakrabarti from BITS Pilani Goa campus, and today I'm going to tell you how to use colloidal particles as Lego blocks to build complex architectures, and I will do that by programming the self-assembly process of these building blocks. We all have seen children playing with these colorful Lego blocks, and these blocks are of different shapes, sizes, and also different colors. So, to build a particular structure, the grooves and notches of one type of block must fit into the groove and notch of another type of block. So, there are very specific interactions between two block types. So, to design buildings and cars and cities with this kind of Lego blocks, the children need two things: A, blocks of different shapes and sizes, and B, specific local interactions that are designable that is provided in that toy set. In this case, the specific interactions, such as the grooves and notches of a particular block type that can fit with only another block type. So when we try to assemble some structures in a microscale or nanoscale also, we need these two important things: a set of Legos and programmable local interactions, designable local interactions. Encoding a set of local interactions into the building blocks which can guide the assembly process, that means which guide the system to a structure of our desire, is known as the programmable self-assembly. Even in natural systems, it is not always that only simple forces like capillary or hydrophobic and hydrophobic interactions assemble a structure. Interactions can be as complex and as specific as involved in protein folding or DNA assembly. Now, in the macro scale, this kind of programmable self-assembly has been exhibited in the swarms of robots with controllable inter-robot interactions. In the nanoscale, DNA origami has proved to be an important technique to fabricate this kind of mechanical joints like hinges, crank sliders, Bennett linkages, and more complex folding and unfolding patterns. However, in the microscale, which is the most relevant length scale for building microswimmers for targeted drug delivery for photonic crystals and micromachines, there is still a lot left to be done. And it is this length scale where colloidal particles becomes the obvious choice as Lego blocks. So once you have these colloidal Lego blocks, you need a specific designable glue that can bind the building blocks in a desired manner. So say, for example, colloids of type A can only bind to colloids of type B or C, but colloids of type B can only bind to C and to D and not to A. So you need to have those kind of specificity. Now, DNA proves to be an excellent candidate for that glue, for the programmable specific glue, as the nucleotides in the DNA molecule have very specific interactions. For example, adenine can only bind to thymine and cytosine can only bind to guanine via hydrogen bonds. Also, at the present time, DNA molecules are completely designable and the physicist just has to provide the particular sequence that he requires to the companies and they will design those DNA molecules with high purity. By choosing a particular sequence of these nucleotide bonds, the interactions between two DNA strands can be programmed or designed in the entire range from attractive to repulsive and anything in between. So we have our Legos and we have our programmable glues. We can stick them together, but it turns out that this is not enough. Because if we throw colloids functionalized with DNS together inside a liquid medium, instead of forming ordered structures, they will form this kind of disordered aggregates. This is because there is no directionality in the system, and the red colloids in this picture here, they can attach at any point on the green colloids. So this is known as the random parking problem, and this cannot be solved by annealing the DNA because the DNA has a sharp transition near its melting point. Patchy particles can be used to solve this, where the particles, say for the red particles, will attach on the green particles only only via some specific patches where it can have some chemical molecules or other kinds of interactions. But those kind of patchy particles which do provide directionality are very non-trivial to make. So we need to introduce reconfigurability in the system so that the particles can move and diffuse and attain a more compact, ordered, defect-free configuration. Also, the reconfigurability is important or interesting from the viewpoint of making flexible mechanical joints in the microscope. So my motivation here is to make designable, defect-free configurable structures that can be utilized for a wide variety of applications ranging from flexible microswimmers, switchable photonic crystals, mechanical joints, and even mechanical metamaterials. So how do we make reconfigurable colloidal joints? Basically, we take these colloidal particles, which may be silica or polystyrene, and coat them with a lipid bilayer. So basically, we make small unilaminar lipid vesicles via extrusion through two membranes, and then we let this vesicle structure on the surface of the colloids, forming a smooth lipid bilayer. And then we insert a DNA construct into this bilayer. So the DNA construct looks like this. It is a 47 base pair long, rigid backbone, stout rod-like part, at one end of which is connected an 11 base pair long sticky end. The other end of the DNA construct contains two cholesterol molecules which are very hydrophobic. So once this DNA construct is inserted into the lipid bilayer, these two cholesterol molecules will love to sit into the hydrophobic region, hydrophobic tail region of the bilayer. Because this lipid bilayer is a liquid at room temperature, we use that specific liquid called DOPC here. Because it's a liquid at room temperature, these molecules, these DNA molecules, have all the freedom in the world to diffuse in the bilayer. So whenever a bond is formed between two colloids, the two colloids have full freedom of reconfiguration. They have complete freedom to reconfigure around each other because these bonds are going to diffuse in the bilayer, thereby providing flexibility. And therefore, when a joint is made, say between one core particle and two outer particles, it looks like this. These two outer particles have complete freedom to configure or reorient around the central particle, and you see that they can move in 2 pi only limited by the geometric constants until they touch each other. And in the confocal microscope image also, you see this bright magenta particle inside connected to these two outer green particles because the magenta and green represent the two DNA strands with two different kinds of dyes. So how do we measure the joint flexibility of these flexible joints? Basically, we first plot the mean square displacement of this angle theta between the two outer particles and the central particle. So we measure this angle theta, and the slope of the mean square displacement plot with respect to time gives a quantity called the joint flexibility J. And we immediately see that this joint flexibility is strongly dependent on the linker density. That means how many DNA you put per unit area on the surface of the colloids. At very low values of the linker density, so less than like 1,000 linkers per micrometer square, the probability for bonding between the particles is negligible. At linker densities higher than this, we find that the joints gradually stiffen up, and above like 10,000 linkers per micrometer square, the joint functionality is almost lost, as you see that this is a very inflexible cluster. So the optimal window to get joint flexibility as well as ensure a large number of bonded particles lies in quite a narrow range. From the log-log plot of the joint flexibility versus the linker density, we see that the joint flexibility varies as 1 by rho cube, where rho is the linker density. So it is quite a sharp fall. This fall happens because more and more linkers concentrate at the junction, because these linkers can diffuse in the lipid bilayer, so they concentrate at the junction and form a bunch of linkers, which we call the bond patch. And this bond patch, as it gets larger, it makes it difficult for it to diffuse through the lipid membrane, leading to an arrest in the flexibility of the system. Now let's look a bit more closely into the bond patch. So what is this bond patch? It is basically this blue region in the schematic diagram. So this is the region where the bonding between two DNA molecules can take place, and Dmax is basically twice the maximum length of a DNA linker. The area of this blue region for two equal size spheres is 2 pi RL, R being the radius of the particle and L being the DNA linker length. Now, this bond patch shows up as these bright regions in the confocal microscope image. You see these white patches, they are actually the bond patch region. Now, if we calculate the different energy terms as per the discussions in this paper, then these energy terms will contain the entropy cost for confining a DNA linker into the patch region, this blue region. So there will be a translation and a rotational entropy loss as well as a combinatorial entropy gain. So we will see that the energy required to form one single link between two DNA particles is about minus of 4 kT. So bond formation is favorable, and also although that the energy is quite close to kT. This value may actually even be smaller and more closer to kT, as we do not take into account the repulsion from the highly dense linkers at the junction region at the bond patch and the effect of stabilizer tech molecules which we put on the surface and so on. The second thing that we take away from here is that the entropy cost for reducing the radius of this bond patch to half of its value is equal to 1.4 kT per linker. And considering that there are about a few hundred linkers in the bond patch, the entropy cost for compaction of the bond patch is pretty high. Now, you can ask the question here that why doesn't all the DNA linkers come together, diffuse through the lipid bilayer and form a complete junction at the patch area so that the entire flexibility is lost and everything is arrested? Why does not that happen? So that doesn't happen because you see, I told you that the energy is quite close to kT, and if we actually find out the melting temperature of our 11 base pair long sticky end, it is about 32 degrees Celsius. So the DNA is expected to continuously bind and unbind. The sticky ends will continuously bind and unbind, and that will provide a sort of a steady state where some linkers are binding and some linkers are detaching. So we verified this using a fluorescence recovery after photo bleaching, a FRAP experiment, where we bleached a portion of the side portion of one of the colloids and also the bond patch region of the colloids. And in either case, we saw that the fluorescence recovered, indicating that the bonds are broken and diffuse away, while new linker molecules diffuse into the bond patch area, making new bonds. So this is what keeps the connection mobile. So now that we have our colloidal flexible connections, let's make a few joints with them. So the first thing that comes to our mind is this spherical joint that I showed you earlier, that the particles have 2 pi radians of motion, limited only by the geometric constraints present in the system. This is in quasi 2D. So if we use lighter particles, for example, polystyrene particles in silica, then the motion will be in 3D, completely on the surface of the core sphere. So this is like a ball joint. We can also create a slider. So say instead of 2 spherical particles, we take a cube and a sphere. So now, as long as this sphere is on one of the faces of the cube, then the bond patch area is extended and it is favorable. However, the moment this particle tries to cross one of the corners or edges of the cube, then the bond patch area has to be compacted to cross over. And I told you that this reduction of the bond patch area by half of its radius leads to an energy penalty of 1.4 kT per linker. So that in total is going to be a very high energy cost. It's entropically extremely unfavorable, so the crossing the corners will not happen. So over time, the particle will tend to remain on one of the faces of the cube, and it will be like a 2D slider. So entropy here creates the slider. We can even take this to 1 dimensions if we allow the system to sediment on the glass surface that we are using, so that the particle effectively has freedom of motion in only one direction. As you see here, they have sedimented onto the glass surface, and there you have a 1D slider. We can also use the topology of the system, not just entropy, to create a hinge. So instead of a cube and a sphere, if you use a dumbbell and a sphere, then as long as the sphere is on one of the outer surfaces of the cube, it has only one bond patch area. But the moment it falls in the west region, it has 2 patch areas. So it is now trapped and it cannot escape to one of the outer surfaces of this dumbbell. So over time, all of the particles diffusing on the surface of these outer lobes will fall into the west region, and the only freedom of motion that they have will be a sort of increasing the distance or decreasing the distance between them while being confined to the west region. So that is like a hinging motion. So topology here creates the hinge. We can continue this further and build even more complex structures from the simple ones, for example, a colloidal polymer. So in this case, we have joined our colloidal joints and made a very flexible reconfiguring colloidal polymer where it will continuously reconfigure, and then in the end it folds onto itself to form a complex structure. We can also make a colloidal molecule, which is basically composed of few colloidal atoms, which, very analogous to real atoms, have some rotational or vibrational degrees of freedom. We can also make floppy colloidal networks, which is like this, and these may be very important for making switchable photonic crystals or colloidal metamaterials. So the 2 handles that are important to get either of these 3 structures is the size ratio and the number ratio. And playing along with the size ratio and number ratio of the 2 kinds of colloids, we can make different kinds of structures. Now, the colloidal molecules are very important or interesting to us from another viewpoint, as they can feed us to form compact structures. So because of the random packing problem, you see, we landed up with structures like this, where we had no way to go to maximum valence structures. Once we get this maximum valence compact clusters, we can use them as building blocks to make even more complex architectures. So the reconfigurability in this system, in our system, actually provides a pathway for obtaining maximum valency in these clusters. And we verified this for a wide range of size ratios. And in each case, we saw that we got the maximum valence that we expected for our colloidal molecules. And we also made a study on the dynamics of growth of these colloidal molecules, where we saw that the growth is actually quite fast in the beginning of the process, and eventually it slows down. Even though the colloids attain maximum valency, the growth has a distinct slowdown at higher valences. So this is mainly because once the core particle surface is saturated with the second or the third particle, then the fourth or the fifth particle finds lesser and lesser amount of space to attach on the surface of the core particle. So there are lesser number of possibilities, or it's entropically more unfavorable for the fourth, fifth, and sixth particles to attach the core particle, especially considering that this is a very short range interaction. And we also verified this with an experiment where you see that the simulations in the experiment basically show the same qualitative trend. So reconfigurability allows maximum valence, but over quite long assembly times. So in summary, we made DNA functionalized colloidal LEGOs, and we showed that we can attain programmable self-assembly with them. We introduced reconfigurability into the system by using DNA linkers which diffuse in lipid bilayers via the cholesterol anchors. We made some flexible micromechanical joints, isotropic ball joints, spherical joints, hinges, sliders, and also some complex structures like colloidal polymers, molecules, and networks. Now, the next step here would be to attach an active particle, or so as to say an engine, with these joints and actually make a machine. We also built complex structures, and we showed that the reconfigurability allowed colloidal molecules to attain the maximum expected valence, thereby solving the random parking problem. So I'd like to thank everyone for giving me the opportunity to give a talk here, and thanks all the audience for their kind attention.